Hello, everyone. I'm glad to see you guys here. Welcome to the Tech Science Press Science and Human Development Lecture Series. Today's lecture is co-organized by the Nanjing University of Information Science and Technology, School of Software. This series of lectures is based on the Tech Science Press original intention. Our intention is to serve science and human progress. In this series of lectures, we will invite scholars in various fields from all over the world. Those cutting-edge scholars will share their latest scientific research with us. As an academic press, we are a bridge. We'd like to make some contributions to spread advanced scientific research achievements and promote academic exchanges. When I was doing research in the computer science field, I was impressed by the grad camp. I was so excited. I contacted the author immediately. To my surprise, he's so young, a young and promising scientist. Wow. I asked him if he could share his research with us. And he said, yes, sure. It made me feel that science has no borders. So here we are. It's a great honor to have Ran here to share with us. And today's host is Professor Yudong Zhang from Leicester University. He was selected to the world's top 2% scientist by Stanford University from 2020 to 2022. Welcome, Yudong.
Okay, thank you. It's my honor to introduce Dr. Ran. So the title of today's keynote talk is Empowering Human Decisions Making in AI Models, the Path to Trust and Transparency. And let me introduce Dr. Ran. Ramprasaath is a senior machine learning scientist at the Atara AI. Prior to this, he was a senior research scientist at Salesforce. He did his PhD in computer science at the Georgia Institute of Technology, advised by David Perica and Drew Batra. His research lies at the intersection of machine learning, computer vision, and language explainable AI, and more recently, the medical AI. Specifically, his research focuses on building algorithms that provide explanations for decisions that emanate from deep networks in order to build user trust, incorporate domain knowledge into AI, and correct for unwanted biases learned by deep AI models. Dr. Ran has previously interned at Brown University, summer 2013, Oxford University, for 2014, Facebook, spring 2017, Samsung Research, summer 2018, Tesla Autopilot, spring 2019, and Microsoft Research, summer 2019. He graduated from Berlin Institute of Technology and Science, Pilani, in 2015 with a bachelor's degree in electrical and electronics engineering and a master's in physics. So now let's welcome Dr. Ran to give us the talk.
First of all, thank you so much for the invite, Lee and Yudong. It's my absolute pleasure to be here. And I'd like to thank everyone who's joined the call today and whoever is listening to the talk. Thank you so much. And let's get started. My name is Ramprasaath, and today we're going to be discussing some works on explaining the decision-making process of deep networks and how understanding this decision process can help us fix various characteristics of the model. And please feel free to interrupt me at any point with any questions or thoughts that you might have, and we can make it as interactive as you'd like for it to be. Yeah, so we are, inching closer towards, having a reality where we have fully autonomous systems that can transport us to our work every day. But when these systems fail, they fail spectacularly disgracefully, leaving an end user staring at an incoherent output, making us wonder why did it do what it did. And we seem to be living in a world where machine learning based mistakes gain a lot more attention than human errors. Pretty soon, these machines might be assisting doctors in performing surgeries. And if the model suggests something out of ordinary, we wouldn't know if performing that would lead to a catastrophic failure, or is it just something really interesting that we have not yet tried? And so we need interpretability in order to build trust into our systems and move towards their meaningful integration into our everyday lives. And this involves building, transparent models that have a way to explain to us why they predict what they predict. And I believe that, this transparency and the ability to explain is useful at, three different stages of AI evolution. First, when an AI is significantly weaker than a human and it's not readily deployable, for example, some visual reasoning task, the goal of transparency and explanations could be to identify the failure modes, thereby helping researchers focus their efforts on the most fruitful research directions. Second, when an AI is, on par with a human and is ready to be deployed, for example, you can take image classification trained on sufficient data. The goal there could be to establish appropriate trust and confidence in users. Third, when an AI is significantly stronger than humans, for example, chess or AlphaGo, the goal of explanations could be machine teaching, like where a machine can teach us humans as to how do we make better decisions. Essentially, in this case, we as humans are benefiting um, from machines. So in this talk, I'm going to talk about my work on explaining decisions made by any deep model. First, I'll talk about how we can, explain these decisions. And next, I'll talk about how can we use the insights that we gained from these explanations to understand, where models are debiased, what models are biased, and try to find ways to debias them. Following that, I'm going to talk about how we can, use explanations as a way for humans to, transfer knowledge to, deep networks. And finally, I would like to, just touch briefly on what I think could be the next, big thing for XAI, explainable AI. So as you can see, in the first part, I'll be talking about explaining model decisions. And in the second and the third parts, I'll be talking about how these explanations can be used to fix various characteristics of the model. So let's get started. What is the question that we're asking? We're asking how can we explain decisions from deep networks? And let's highlight the word explain and try to break down and see what we mean. We are specifically dealing with visual explanations in this line of work that I'll be talking about today. A visual explanation, tells us where does the intelligence system look when making decisions. And, let's look at the kind of tools that we had before GradCam came. There were works, that were gradient based, like backprop, guided backprop, layer-wise relevance propagation, integrated gradients, and so on. And there are works that, would simplify the model architectures, like class activation mapping, and there have been works that consider this model as some kind of a black box, like essentially like Lime, SHAP. So they don't essentially care about the underlying model parameters, and instead find a way to explain these individual decisions. So, all these, approaches had some problem that they might either be noisy or not class discriminative, or, they might not help us, understand this particular model that we are trying to explain. And we'll discuss why that's the case later. Let's introduce GradCam here. So given an image, we feed through the convolutional layers of a CNN, and these will give you, feature activation maps. And these maps can be used for any, task specific, any task. And, let's take some examples here. Let's say you have an image classification network where you might, on top of the last convolutional layer, you might have one or two fully connected layers. And let's say the model predicted the category tiger cat. Now we are asking the question, why did the model predict tiger cat? What in the image is it looking at to predict tiger cat? So the first thing that we are looking to do is to figure out what are the most important neurons in the last convolutional layer that are useful in predicting this category tiger cat. And the way we do that is by simply computing gradients. Essentially, we're computing the gradients of this particular logit corresponding to tiger cat with respect to the last convolutional layer. And this will give us, gradient maps that are of the same dimension as your image, as your input activation map. What we do here is we do a global average pooling here. And what this global average pooling does is tells us what is, how important is one neuron. How, for example, this weight, W1 will tell us how important the first, neuron in the last convolutional layer is for predicting this particular category of tiger cat, and so on. You can do that for all the neurons in your layer. Now, we have figured out what are the neurons that are important for tiger cat. Now we want to explain this particular image. And what we do is we just do a simple weighted, sum. Essentially combine each of the forward activation maps through these weights that are computed through these, gradient computation, and add those and sum along the channel dimension and remove the negative values to get GradCam. So this activation map would be of the same dimension as your last convolutional layer activation. So essentially, in case of VGG16, it can be, like 14 by 14 map. Now, what we can do is we can, just interpolate it to the size of the image and, visualize it. And you can see here that the model seems to be looking at the cat regions. As you can see, the cat is, below the dog. It's looking at the cat regions to predict tiger cat. Now, you can do this for any task, right? What did we do first? We just literally computed the gradients all the way from the final output to the last convolutional layer. So essentially, whatever network you have post your last convolutional layer, you should be able to, just use that. You should be able to compute these gradients. You can have image captioning where you have an LSTM here that predicts a cat laying on the ground. Or you can have, a question, for the case of visual question answering, is there a cat? And the model, can say for the answer yes, where is the network looking at, and so on. Or you can actually do this for anything that's differentiable, going from the convolutional layer to the final output. And that's the case for almost all networks that we train these days. Because we're training them through gradient descent, and so it is differentiable. Now we can even go beyond this to do guided backprop. Essentially, if this image might be hard to see for people who cannot see, I can explain this. Here you see, what are the regions that are in general useful for the network, and they don't specifically care about which class that image is about. So here you can see both important regions of the cat and the dog that are highlighted. Now you can just simply dot product them to get guided GradCam, and here you can see that it looks at the cat regions. Not only that, it's this particular variety of cat, tiger cat, and you can see that it actually looks more on the striped regions. And you can do this for any class, even the class that your network did not predict. You can now, let's say, boxer is one kind of dog category, and now we can say like, oh, there is a boxer here. Can I, predict where would the network have to look at in order to say boxer? And you can see that the network, is able to now highlight the dog. So let me see if there are any questions so far, and then I can move to the next slide.
Okay, so let's ask, are there any questions from our attendees?
Okay, feel free to interrupt me at any point.
Dr. Ram, may I suggest that we can let the attendees to ask questions after you finish all the talk?
Oh yeah, sounds great. That's perfect. Yeah, sounds good. Now let's see. Now that we have a way to get explanations, what insights can we gain from them? We visualized one of the earliest deep network-based captioning systems. For this image, the model predicted like a group of people flying kites on a beach. And this is where the network is looking at. And you can see that it seems to be looking at the flying objects and a little bit at the people. And for this image, the model predicted a man is sitting at a table with a pizza. In fact, you can see that the man seems to be looking at the model seems to be looking at the man and a little bit at the pizza, but there is no evidence to suggest that the person is sitting. Indicating that as a language model, it can be taking over and hallucinating things. Here is GradCam applied to visual question answering, where the task is given an image and a natural language question, like what is the person hitting? The model seems to be looking at the ball and uses a little bit of the context to answer tennis ball. So we find that even simple non-attention-based CNN and LSTM models tend to look at appropriate regions, and this might even indicate that you might not need attention-based models if your model is strong enough. We can also use this GradCam to analyze failure modes of networks. Like here, the model predicted this to be a car mirror. It's like if someone just showed me this prediction, I'll be like, why is it the case? I don't understand. But then if I look at the explanation, then I'll be like, oh, I see. Yeah, this kind of makes sense that, It's highlighting the round regions around the main categories. So yeah, sure, it could be a card mirror. Now you can also visualize the ground truth category volcano. And if you want to visualize that, you can see it directly looks at the volcano regions. And here the model incorrectly predicted this to be a wine snake. And you can see that it was looking at the snake-like regions. But then you can also, if you give it the ground truth category coil, it can still localize that. So what we learn from this is that even unreasonable predictions can sometimes have reasonable explanations. And we do have a demo that's hosted here, or a video of this can be found on YouTube. And people have extended this for videos. Here's a class that's called Uncovering Something. You can see that the model seems to be looking at the regions even before the person removes that, suggesting that it kind of knows what are all the possible regions that can be uncovered. And similarly here, pushing something, and as the person's hand approaches close to the device, those edges get highlighted. So these are all interesting ways to see how your model is doing. So initially we did this for CNN-based models, but then later we extended it to even beyond CNN architectures to multimodal transformers. This is our newest paper where we introduced a vision and language pre-training framework called ALBEF. And here are some visualizations from ALBEF. Here, a little girl, for the caption, little girl holding a kitten next to a blue fence. We can see that the attention for the girl is looking at her face, or holding, it seems to be looking at the regions of the cat. And interestingly, for the word next, it seems to be looking at important regions around the girl. It seems to start looking at the fence already. Here, same thing, we can do this for VQA. This is the rice noodle soup. And for the answer, yes, you can see that it seems to be looking at the rice noodles. And what is to the right of the soup? Chopsticks, and attention solely seems to be at the chopsticks. Here, what is the man doing in the street? For walking, you can see that it's looking at the legs of the person. And what is the truck on the left sell? Ice cream, and it looks at the ice cream truck. So yeah, these models, even though they're not trained, even though they're not trained with any pixel level supervision, they seem to be, doing things, fairly well, and through GradCam, we're able to figure out, how they're doing. So it gives us a sense of security. So yeah, coming back to, the initial slide, the 3 stages of AI evolution, I would like to think that in spite of what some positive examples that we've seen, our models are still in the first regime where humans are still versed in AI. And let's see for this regime, how can explanations help improve various aspects of the models. So as you can see, until now, we were only using interpretability to establish trust with humans, understand the failures. But I wanted to, see if we can do something more. Can we use this tool to understand the biases that might be learned by models and somehow debias them? So that's the second word that we want to talk about. So can interpretability help in some way? And here, one of the works, this was by Lisa et al. And they used these explanations to overcome gender bias. For example, this was work that was called Women Also Snowboard, Overcoming Bias in Image Captioning Models. Here we have an image captioning model, which given this image, it incorrectly predicts a man sitting at a desk with a laptop computer. But if we visualize where is the model looking at when making prediction for man, GradCam seems to highlight the computer. But what do we want? We want our models to, predict the gender correctly, and also point to the woman. So this will help us say, the model is right for the right reasons. So these are the kind of models that we want. So it's important to think about the reasons why our models might be making certain predictions. Because sometimes you can be right, but you can be right for the wrong reasons. And so here's a baseline model that says a man holding a tennis racket on a tennis court, right? That's great. But then it's looking at the tennis racket. So you can see that it's right for the wrong reasons. And this might be concerning because even though your sentence metrics might say that you're doing good, you might be a little bit worried when deploying this system that's looking at the wrong evidence. In contrast, our model is going to be, going to talk about the gender. It's actually going to be looking at the model here, at the man here. So they at a high level, they just introduced an equalizer model, that takes a generic captioning system, and you feed in words of an LSTM and then train this through normal cross entropy loss. In addition, they also introduced a confidence loss, that does encourage the model to be more confident about predicting the gender term. So here you can see that there is a person here, and there is clear gender evidence. And so we want the model to be confident in predicting that gender. Right. And then when the gender is blocked out, for example, you just block out the regions of the person, you want it to be less confident about the gender, and it should resolve to, gender neutral words like, person, and so on. So yeah, there's an appearance confusion loss here. So when you do this kind of thing, you can see a model that was initially saying a woman holding a cat in her arms. Now it not only says a man is holding a black and white cat, it also looks at the man. Similarly, a man sitting on a couch with a laptop computer, even though there is no evidence of man, now it says a person laying on a bed with a laptop. In this work, we're going to talk about the work on how explanations can help tackle distribution shift. And this was an ICCB work called Taking a Hint, Leveraging Explanations to Improve Grounding in Vision and Language. So vision and language models have this problem of using statistical correlations in the training data to arrive at decisions. Like if you give this image to an image captioning model, more often than not, it might say a giraffe standing next to a tree. And that could be because most images of giraffes in the COCO training set has them surrounded by trees. Here, what color are bananas? It might sort of saying yellow, because most training images in the data set have yellow bananas. So our lab had introduced a new split of the VQA data set where they explicitly changed the distribution of the train and test and found that models perform poorly. Our lab also went ahead and collected a data set for a small subset of the VQA data set, where people were asked, given this blurred version of the image, and asked a question, what room is this? People had to unblur the regions and say the answer. Now, this gave us a way to get where do humans look at when making decisions? So our approach is called HINT, Human Importance Aware Network Tuning. So essentially, if you take this network, that uses these proposals, like now you can say these are the things that you need to be looking at, and that is going to make the models much more, grounded, and it's going to now look at the, which room is this? Initially, it was saying dining room, but now for the now it might be looking more at the kitchen, and it might actually be looking at the kitchen, the regions that are indicative of kitchen, which are the stove, the microwave, or the fridge, and so on. We did this on a data set that's called VQA-CP, and where we saw a 7% improvement over standard VQA performance. And what this says is that making machines look at regions similar to humans would make them generalized to arbitrary distributions much better. And we also applied this for image captioning models, where we see that a baseline that's looking at the sink to predict toothbrush is now correctly looking at the toothbrush, and only at the toothbrush. And similarly, a woman with a tennis racket with a cat in the air. And it's interesting to see that the model is able to look at the cat. In fact, the shadow of a cat. So as you can see, the attention seems to be improving much better. So yeah, now we're going to talk about work that uses explanations to improve representations learned from a self-supervised model. So this work is called casting a model, learning to localize improved self-supervised representations. This was work at CVPR. So contrastive learning aims to learn visual representations from unlabeled images through the task of instance discrimination. While some of the recent methods have begun to outperform, fully supervised ImageNet retraining on several tasks, unfortunately, their success has been confined to unlabeled iconic ImageNet-like images. Naive application of these approaches to uncurated web images has only shown marginal gains. So in this work, we analyzed contrastive SSL approaches to understand the cause of this limitation. Why does it not work on complex scene-level data sets? And we actually tried to understand this question. So first thing we found was they have poor visual grounding ability. For example, when we use GradCam to understand which regions the model relies on to match the query and the key regions, the model seems to be looking at the grass more than that of the dog, leading us to realize that these models rely on low-level visual cues or spurious background correlations. These are not something that we want. And another thing is, even during the crop computation stage, taking random crops from an image may be acceptable for iconic images, but when you have a complex scene level image such as this, like they might receive some imperfect supervisory signals. Here the query can be sampled from one part of the image, and the key can be sampled from a different part of the image, and they might look like completely different scenes. So this might discourage semantic understanding. Yeah, so we argue that these two issues maybe explain the diminishing improvements of contrastive SSL models trained on web scale images, and why they might be showing a reduction in performance when training on complex scene level images alone. Yeah, so to fix this, our first contribution is to introduce a semantic alternative to random cropping. So we introduced a intelligent geometric transform. Let's say you actually have an image and an unsupervised saliency map that indicates what is the most important region in this particular image. Now we devised a transform that's called saliency constrained random crop. So essentially, if you take you first sample from the unsupervised saliency map, two regions such that they are overlapping, and they are overlapping such that the main region of interest is also present in that overlap. And we had some area constraints here. Similarly, you do that for the original image, which will end up giving you two crops. Not only does it give this, it also gives us crop-oriented saliency maps, which can be used for supervision. And we'll talk about that in the next slide. So now we turn to our approach cast. The idea is pretty simple. The idea is to just make models attend to appropriate salient image regions during the contrastive pre-training stage. So we show cast in the context of MoCo. So given an image and its saliency map from an approach called deep USPS, through our saliency constrained random cropping strategy, we get a query and a key crop along with crop-oriented saliency maps. We pass the query and the key to their respective encoders. The momentum contrastive loss now tries to get the query and the key representations closer, but further away from a queue of negatives. With the masked key that is containing the most salient region in the key crop, we can then compute the gradient of the dot product of the query and the masked key representation. With respect to the last convolutional layer activations of the query encoder, this gives us GradCam. Basically, we need to be average pulling the gradients and combine them with forward activation maps to obtain this image that's GradCam. And here what you can see is the model seems to be looking at the regions in between the sheep more than that of the sheep. Now the model seems to be looking at the background regions and not the sheep that we would have liked. So we provide a cosine similarity based attention loss. This is to align GradCam maps with the query aligned saliency maps. And these two losses are combined to form our cast loss. And the model upon convergence, you can see that it now looks at the sheep regions much more than anywhere else. Yeah, and this is what we wanted, right? Now, what we observed was, in addition to outperforming MoCo on all the tasks, linear and fine tuning, we saw that cast pre-training on Coco, which is a 10x smaller data set, even outperforms ImageNet fully supervised pre-training on all the fine tuning tasks. And we also found that this improved grounding during pre-training also transfers to downstream tasks as well. Note how the ImageNet fully supervised model and MoCo uses the background as well to predict the ball player, whereas the cast pre-trained model only looks at the player. And we also find that cast models attend to the whole extent of the object, as you can see here. And then, in order to test the robustness of cast, we evaluated it on the background challenge data set, where the backgrounds of ImageNet images are replaced with various settings. As can be seen, the cast pre-trained models significantly outperform on all the settings, even achieving close to 13% improvement. For this, here's an example. For this image of a bird, when you actually replace the background with water, the baseline model changes its prediction to fish, whereas cast pre-trained model still predicts bird. And here, this relies on the background. It basically shows that it relies on the foreground regions more. And similarly, when the background of this reptile class is changed to a place where musical instruments typically occur, the prediction of cast pre-trained model does not change, whereas the MoCo models thing changes. This indicates that cast makes models resilient to any kind of background changes. And this year we also had an extension of this to videos. It's appearing in WACME. Basically here you can see that in case of videos, this problem of background remaining the same can be a big deal. Temporal association might lead to inconsistent semantics when you sample positive and negative pairs. So we find that if they are true positive pairs, like if you look at where is the network saying when taking two different regions of two regions in a video, two short clips of a video. If you're trying to figure out where is the network looking at, it seems to be looking at mostly the background, and it's very well spread. But that's not what we want our networks to learn. We want the networks to be focused more on the foreground, and our representations to be of the foreground more than that of the background. So we propose to utilize an unsupervised tracking approach here. So essentially, we designed a novel sampling strategy that utilizes unsupervised foreground tracking for videos, and I'll get to how are these sampling strategies work. Starting from a 10-second video clip, from a particular data set called kinetics, we compute the unsupervised tracking to acquire binary mask that represents the foreground. Later, we filter out frames that don't contain the foreground mask. And then we perform positive pair sampling to sample short video segments from this entire video. And these are the positives, and the negatives will come from a completely different video. So this essentially ensures that there is some foreground that is, constant across the video. Now, once we get these positive pairs, previous works usually do random cropping, but we said to introduce some kind of spatial constraints, just like what we did for cast, the earlier work. So in the end, we would acquire positive pairs that represent the same concept. We then trained the models with two losses, just like we saw before. And once the loss is backpropagated through the encoder, we update the weight of the, the frozen encoder. And here you can see that you can also find a way to get the attention heat map, just like what we did earlier, where you take the gradients of the dot product of the two representations with respect to the last convolutional layer. And here you can see that it seems to be looking at the regions of the bike. Now you can guide this model through an attention loss, just like we did earlier. And essentially what this is doing is to guide the encoder to focus more on the foreground regions. And then we backpropagate these attention loss to improve the encoder. And there are two ways to evaluate our learned representations. Like in the transfer learning setting, we use the learned representation as a learned backbone during pre-training to initialize the weights of the model, and later we fine-tune on the human labeled data set and evaluate the performance, such as video action recognition. And in the other case, a fixed feature setting, we can actually use the extracted feature directly for downstream tasks without fine-tuning the encoder. And you can do this for tasks like text to video retrieval, and so on. We evaluated our models on various downstream tasks, including action classification, video retrieval, and we achieved state-of-the-art compared to previous methods using the same backbone. And to evaluate the robustness of the model, we evaluate on a newly constructed video backgrounds challenge dataset. This is an action classification task where we want to predict the class label, and essentially we did this by replacing the background or removing the foreground. So the intuition is that the predicted action label should be the same regardless of the background. For example, we should identify the action as combining hair even when the background changes. So our model shows that significant improvement when there is a significant improvement when the foreground exists, and the performance drops the most when the foreground does not exist, and there is only the background. This shows that our models rely very less on the background signals. And we also evaluated our model on video segmentation tasks to demonstrate the grounding. And this task is given the entire video along with the mask and the first frame. Essentially given the entire video and the first frame's mask. The model just needs to predict the entirety of the mask across each frame. Essentially, you're tracking an object of interest. And you can see how good Moco Privilege does, compared to previous approaches. Yeah, let's look for some examples. This video should be playing. You can see how the base model seems to be, going all over, but our model seems to be looking right at the, person who's kayaking. Here, a person jumping. You can see the focus has been on jumping throughout. Here, it seems to be looking at the, building. And here, the model seems to be focusing on the foreground and tracking the person quite well. So yeah, so far I talked about how can we explain decisions from deep networks, and how can we use these explanations to understand when models are biased, and make them look at appropriate regions and thereby debiasing them. Now we are moving towards the next line of work, where we are trying to see if the model can benefit from human-like compositional reasoning. So this work is squinting at VQA models, introspecting VQA models through sub-questions. We design VQA systems for us to be able to have useful, meaningful conversations and help us with everyday activities. If a blind person is coming and asking, taking a picture and asking, is the banana ripe enough to eat? The model might be saying, yes, it's ripe enough, you can eat it. We're like happy, but then if you ask another question just to be sure, is the banana mostly green or yellow? And it might say green. You're like, if you thought the banana was mostly green, why did you think that it was ripe enough to eat? So it seems to be answering a more complicated question about ripeness, but seems to be failing on things that it should be using to talk about ripeness. So that's what we're looking to address. So we introduced this new data set that's called VQA Introspect. So we essentially showed humans an image and a question that requires reasoning, and asked them to provide perception-based question-answer pairs that were useful to answer the main reasoning question. For example, here, given this image and a question, is this a keepsake photo? And for the answer, yes, our annotators gave these following question-answer pairs. Like, is this a black and white photo? Is the woman wearing a white veil and holding flowers? Here, is this giraffe at the zoo? More for the answer, yes. People seem to be talking about the fence around the giraffe, or if the grass is shorter than 3 inches, and so on. Here, does this appear to be an emergency? People talk about the existence of a lot of ambulances or a fire truck, and a lot of people standing in the middle of the street. And is this a good idea for a rainy day? For the answer, no. People talk about the existence of the roof over the vehicle. So we evaluated current models through, across 4 quadrants. And we saw that around 28% of the times, the model is right, but for the wrong reasons. So we introduced a new approach, that's called Squint, sub-question importance aware network tuning. So for the question, what season is it? We essentially make the attention for the sub-question, like, is there a Christmas tree pictured on a cell phone? Like, essentially, we introduced an attention loss here. that makes the model look at the regions corresponding to the sub-question to answer the main question. And then regular, cross entropy loss. Essentially, this is saying, if you now look at the sub-question attention, are you able to answer the question correctly for the main question? Ideally, you should be able to, because the idea of the sub-question is to be useful to answer the main question. So yeah, we find that this approach improves the reasoning ability of models and makes them, much more consistent. So this says that, human-like compositional reasoning can help machines reason better and be more consistent. So this is an extension that we presented at NACL, where we introduced the concept of relevant and irrelevant sub-questions for answering the main reasoning question. And we introduced contrastive gradient-based loss. And again, we saw that these kind of models are able to now understand what are things that might be useful for answering a question, and what are things that might not be useful for answering a question. So far, to summarize, we talked about ways to explain the decision-making process of deep networks. And we talked primarily about GradCam and how we saw how it can work for CNNs and even beyond, transformer-based architectures. We also looked at how we can use the explanations and, debias networks. We talked about how we can incorporate human knowledge and transfer these knowledge through explanations to improve networks further. Now, very briefly, I wanted to talk about what I think is next for an explainable AI. As you might be, seeing large-scale language modeling has gained a lot of popularity, and I feel like there is a lot of impact that it can do in the explainable AI space as well. I think LLMs can be used to better understand what the model parameters capture. I feel like LLMs might even be able to, help us understand what is each parameter in the network capturing. So as LLMs capture, learn complex patterns and relationships between data, and this makes them well suited for understanding and interpreting, the internal workings of models. And I feel like these LLMs can even help provide feedback to models. Like I think LLMs can there are some open questions here. Like, can LLMs be used to improve the model performance by somehow adjusting the weights? Can we provide language feedback to models and make them much more human-like? So these are some open questions that we can be thinking about. And I think with that, I would like to conclude this talk. So please let me know if you have any questions, and if you don't get to ask your question now, my inbox is always open. I'm happy to have any of these discussions, collaborate, and I'm also on the market for new positions. So I would love to know if you know of any opportunities. I'd love to know more about it. So thank you so much, everyone, for coming, and I'm happy to take any questions now.
Okay, thanks, Dr. Ren, for your excellent talk. Now, so all the attendees, if you have any questions, you can feel free to unmute your microphone and directly ask here, or you can drop your questions at the chat box. So, Ren, you can see from the chat box there is a there's a question asked from our attendee. He says, "Thank you for the very interesting talk. GradCam has been widely used in computer vision tasks. Can we use other conf layers like the CNN to understand each neuron for decision of interest and produce the activation heat maps?"
Yeah, that's a fantastic question. In fact, that has been a question that has been on so many people's mind when GradCam was introduced, because as I said in the slide, we have only managed to get this to work for the last convolutional layer, which means the resolution is going to be limited by that factor. That said, why is that the case, right? If you think about what we are looking to do when computing GradCam, we are looking for the most semantic neurons. Essentially, we are trying to, at the end of the day, we are trying to explain to humans. And there's been a lot of work that showed that the later layers of a CNN capture much more semantic concepts. And earlier layers, might not be, capturing semantics. It might be mostly, be building structures that later layers can use to get something semantic. And I believe that is the reason why GradCam works best for last layer only, and not further. But I believe that there is a lot that can be done, in terms of expanding this work to understand each neuron, even in the context of understanding how, like now, given the last layer neurons, can I go back and see the last layer was looking at the dog's ears, but what are the features in the previous layer that led it to look at the ears of the dog? Like what neurons combine to form a dog ear neuron? So those are interesting questions to ask and answer. And now more than, we have mostly been using transform-based architecture. So everything attending to everything else. So these things can be working very differently here. So I think it's definitely worth looking into this. Yeah.
Okay. Thanks, Ren. So are there any other questions from the attendees?
Hello, can you hear my mic?
Yeah.
Yes.
Yeah.
Audible.
Yep.
Very clearly,
Yep.
you are audible.
Yep. Thanks for your excellent presentation, Dr. Ran. So actually, I have three questions. So first question, for the explainability of the AI models, for our CV era. So, for example, in self-driving car, assume that we can train an accident object detector to recognize the car or human. But I mean, for us, instead of recognize, okay, this is human, this model, AI model can recognize the human and car. For more, I think we want to know that whether this AI, whether this model can, okay, this human, we need to avoid it. For that car, we need to, for that car, we need to okay, this is car, and for that human, we need to avoid it. So I want to know that whether it's possible to to extract more informations behind far from the camera, not only the object over there, but for more, we want to know, okay, whether this AI can recognize this is human, and we need to make sure this car can avoid it. This is the first question.
Mhm.
Yeah.
Yeah. So that's great. Couple of things, right? I think this is what this is an advantage that GradCam has over regular attention. So regular attention that is feed forward, there is no sense of class. What that means is, given any image, if you take any attention based network, it might be highlighting everything that is important in an image.
Yes.
Not just like a person or a car. It might just be highlighting everything that's important, all possible things that it has seen in the data set, ideally. But GradCam, on the other hand, you are computing this in a backward fashion. So what you're doing is you are computing the gradients of the class with respect to the last convolutional neurons. And what that means is you have the ability to say which class and then determine what the network might be looking at. So in your example, you could say, okay, are you able to see a person? And so what GradCam can do is use the label person and then filter out just the regions that are useful for predicting person. And similarly for car.
Okay, got it. Yeah. So another question is that, yeah, thank you. So another question is that okay, so our CV era, I think most of us already use the Grad camera, right? But since ChatGPT already available for us and AI, I think ChatGPT somehow is better than human in some aspects. I think whether it's possible to deploy a jet-like Grad camera, whether it's possible to deploy some kind of the algorithm or something to can be deployed on the NLP era, because because all of us will know that later on AI will be more complex, not even in the CV as well as NLP, right? I think in the future that might be AI he can speak, he can also recognize objects as well. But whether it's possible, we can do some works on the NLP era to decide, okay, this AI will never do some very dangerous action or something.
Oh, that's a great question. I think there is a lot of scope for explainability in the conversational large language modeling space. In my talk, I mostly talked about how can LLMs help with explainable AI. I think the other way is also certainly interesting, like explainable AI helping LLMs, and the use case that you had suggested, I think is an amazing use case where, like nowadays, any mistake the model does, you attribute it to, oh wait, I don't know, it's not working the way I want it to work. I don't know if I can trust it at any point of time. And there are a lot of issues around it. Now, can we use explainability to fix that? And here's an idea that I have. Can you? I mean, at the end of the day, what ChatGPT anything is doing is, with the amount of parameters that it has, it's simply kind of putting together the input data in interesting ways, right? Can you now determine what that input data is? Like through explanations, can you highlight what are the important data? Like for example, you can understand what are the weights that play the most important role, just like we did in GradCam. Now that we understand the weights, now can we go back and now go back one more step to figure out, can I understand what that weight was highlighted the most by, in the training set? So that's another thing that you can do, right? Like you're going, you're essentially explaining in terms of examples that the network has already seen.
Yeah, got it. Thank you. I think for us AI people, we think, because we all say that AI will powerful than humans, but if we focus on the explainable AI, we will let AI to do any dangerous thing, right? So it's very, we need to consider this, even in CI era as well as the NLP era. So even currently we are talking about the ability of AI is less than human, but later on we will see that okay, the AI's ability were more larger than humans, and actually we don't know how it will look like. Maybe the GradCam detected by AI even we cannot understand, right? I think it might happen. Yeah. So I think maybe we can later on we can first focus on some works about okay, how to avoid AI to do some dangerous things by doing explainable AI. Thanks for your answers. Thank you for your presentation. Yeah, that's all my questions. Thank you.
Thank you. Great questions.
Okay, thanks, Jerry, and thanks, Ren. And dear Ren, you can see from the chat box there are many other questions. And the next question is from the William. And the William one says, thank you very much for your wonderful presentation. GradCam is an impressive technique to improve the explanation of deep learning models. It helps a lot to build the trust of people in AI. Since the gradient map can reflect the focus of the models, can we use that from different layers of the neural network to prune the neural network and to reduce the computational costs?
Certainly, great question again. Most of the network might not be used for a particular task that we might be using later, right? So certainly it might be much more useful in case of these large scale models, large language models, which have so many parameters. Can you now get a subset of the network for a particular task and make it much more cheaper to compute? Certainly possible. And I think one way to do that could be, for any task, any new task, you can literally just compute what are the most important neurons in this entire network, right? And only just take, you can basically choose maybe 50% and be like, okay, can I just, based on the weights of GradCam, can I just ignore 50% of the neurons in each layer and try to replicate the same thing the network is doing? I think there is a lot of scope there. Yeah. Great question again.
Oh, okay. Thanks, thanks, Ren. Okay, the next question is from AAL. AAL says, may I ask, when people make decisions about anything, what is the fundamental method of the AI model to make the fastest and most accurate decisions? And which software did you use? What is the general process of operating the software? Please provide the software download URL. And his second question is, the AI model helps people make decisions. Why is it trust and transparency? Trust and transparency here, specifically who or what? What exactly is the root cause?
Yeah, great question. So, like what does the AI model use to make accurate decisions? First of all, I don't know if we can call that accurate decisions. right? I mean, the model confidence might be, very misleading. So it's very hard to say if a confident answer is, accurate even. That said, I think, um, you know, um, essentially it's just trying to, uh, mimic mimic the way it's trained, right? Essentially putting together examples from the training set and trying to find, like, in a very high dimensional space, what is it closest to in the training set, and what is the label that was used during training. Regarding, the software that we've been using, I mean, when we worked on GradCam, we were working on, this thing called Torch. But right now, there is PyTorch, and most of my work, almost everything after GradCam, I've been working on PyTorch. And PyTorch is extremely well documented. It's fairly easy to use, I would say, and there are tons of um, things available in the web, to tutorials available to understand this, understand PyTorch. You can just search for PyTorch and you might be able to get that. The AI model helps make decisions, trust and transparency, and trust is trust. I essentially, through GradCam, we have been trying to make the decision-making process more transparent. And anytime when you make something transparent, I believe that it somehow makes makes it trustworthy as well, because now I'm not blinded, right? Like I can see myself. Why is the network doing something? And I think that's what we are hoping to get through making networks more transparent. I do hope that we get to a place where it's not just just because a model is revealing its entire decision making process, we take it for granted, and blame it for anything that it does. I hope that it's a feedback process at the end. In fact, if you see, most of my projects that I talked about was, how do we take an explanation, take a model and improve it? Like, what does understanding the decision-making process get us? To me, it's mostly this feedback process where a human can now go ahead and fix it. Yeah. Yeah.
Okay. Okay, thank you, Dr. Ren. So we can see the next is another question from William. Says, sorry, one more question. What could be the most efficient action you think to take when we detect a model is making the correct decision for the wrong reason?
Oh, great question. Great question. Again, this, this is something that I talked about in my talk. If the model is saying the right things, your metrics, the things that we capture, might not be addressing all those aspects. I believe we need to be, that's why it is important to construct new metrics that are not just accuracy scores. I think these new metrics should capture robustness, and evaluate models along so many dimensions. And yeah, I think those metrics can help us, when we keep track of all these metrics, we can now, optimize for like best performance along most of those metrics, not just, one metric that might lead to the model doing pretty good. So like, just to answer this question, if the model is making the correct decision for the wrong reasons, I think a human should be intervening and fixing these models, either by fixing the training data or by, understanding why the network is saying something and provide direct feedback over that. Yeah.
Okay, thanks, Ren. And then the next question is from Jing Hua says, thank you for your most inspiring talk. Your method, GradCamp, has been fundamental to our research and development of applications. May I ask for your thoughts on the prospects of active or inherently interpretable neural networks, such as the prototype typical neural network?
I think, certainly, there are certain networks that are inherently, interpretable. My research focused quite a bit on how we can like take any network and make it interpretable. Like if your network is inherently interpretable, sure, I think there might be much more ways to fix it, like than what a network that is only post hoc explainable might help you do. So yeah, I think, for example, you can like, since your network is inherently interpretable, you can go ahead and change the training process to make it, you can introduce constraints at so many levels, not just at the end, like what we are doing in the networks that I presented.
Oh, okay. Thanks, Ren. And we can see there's another question from the Eden Wu saying, can we see human-like decisions used in CV as some kind of improved attention mechanism or image masking technique? And thank you for your impressive lecture.
Can we see human-like decision used in CV as some kind of interesting. Yeah, that's an interesting way to think about it. It's an improved attention mechanism. But I mean, attention, if you're talking about in the feed-forward sense, attention essentially just says, what are all the things that are important for a particular for a particular network? And GradCam is a way to do this at an individual, at a class level, right? So yeah, I think it's just terminology, what we call as attention, what we call as implicit attention. And regarding image masking, sure, if you are, at the end of the day, if you are using these to mask out regions and do something with it, sure, but I mostly interpret this as a way to just understand how these networks work. Yeah.
Oh, okay. Thanks, Dr. Ren. And due to the time limit, there's a last question from Jiaji Wang. And he said, thank you very much for your excellent presentation. There is no doubt that GradCam is very important in AI learning. Three-dimensional medical data often contains a lot of information. Is it possible for GradCam to be applied to three-dimensional or higher dimensional data in the medical images?
Oh, certainly. Three-dimensional data, yeah, I have seen work that has done that has applied GradCam to three-dimensional data problems. Yeah, I think at the end of the day, there is no limitation here. You are essentially computing the gradients with respect to the last convolutional layer. Now, these activations of the last convolutional layer would be, initially we had h by w by number of channels. Here you'll be h by w by depth by number of channels. So essentially you will just be adding another dimension to the GradCam computation, and and your end GradCam result is going to be a 3D volume. I have no reason to believe that this will not work. In fact, right when I was working on GradCam, I did see works that have extended it for three-dimensional structure prediction problems, not in the medical domain, but in but in other domains, but certainly possible in this domain too. Yeah. Yep.
Okay, thank you. Due to the time limit, we can't let the attendees to ask any more questions. If you have any questions, feel free to contact Dr. Ram directly, because we think we can Google Dr. Ram's email and drop any messages to you. So now we are going to do the closing sections. And thanks again for today's excellent talk given by Ram. And
thank you everyone for attending, and special thanks to Yudong and Lev for inviting me for this.
Okay, and today Ram's talk includes the three most important elements in the nowadays AI development: the human decision making, the trust, the transparency. And you can think, to judge from the hype, AI is inches away from ripping through the economy and destroying everyone's job. However, today Ram's talk shows us we don't need to trust AI until we build systems that can earn trust and transparency. I just received hundreds of messages from our attendees to the back end of our assistants, and all the attendees, they said that today Ram's talk has opened a gate for their future research. So thanks again, Ram. I will transfer the microphone to Lei. She will give us the closing speech.
Yes, thanks for today's excellent talk from Ram and the organization of Yudong. It is my pleasure to announce the end of today's meeting. It's a great meeting, everyone. I think we covered really a lot of important items in AI. Particularly, I would like to appreciate the effort from our workmates in the publisher, Tech Science Press, and our journal, CMC, Computers, Materials, and Continua. Thank you for your attention, and welcome to join our following lectures. Wish you guys have a nice weekend. Bye-bye.
Thank you.
Thank you, Ram. Thank you. Thank you, guys.
Thanks, friends. Thanks, Lei. Hope that we can meet in our next session of talk. Bye.
Yes, bye.